And now we can take a look at C. Now, right here we've got a product of two variable expressions. And we've said that the derivative of a sum is going to be the sum of derivatives, but we haven't said the derivative of a product is going to be the product of derivatives. So right here, what we're going to do is we're going to say, first, can I rewrite this function in a way that I know I can take the derivative? And of course, what we can do here is multiply this guy out, right? So right here we can say f of x equals, and then if we multiply this guy out, we're going to get 2x cubed plus x squared plus 6x plus 3. Now, we can take the derivative of this guy pretty quickly with the power rule, and we would get here 6x squared plus 2x plus 6 as our derivative, right? And right here, we know that this is the derivative of this statement. We rewrote our product, expanded out, basically did all the multiplication here, and then we took the derivative of this form of our function, and we know that this is going to be the derivative, right? Now, right here, we can sort of test that idea of the derivative of a product being the product of derivatives by just taking the derivative of the two things that we're multiplying and seeing if it looks like it's going to be the same as this guy. So right here, we can say that if the derivative of a product is the product of derivatives, then right here our derivative would be 2 times and then 2x. A statement that is clearly not equal to our actual derivative. So right here we can say that this, in fact, is not the case. We cannot say that the derivative of a product is the product of derivatives. And this leads us to our product rule. Now right here, what we're saying is if we have a function that is the product of two variable expressions, two expressions involving x, in this case we'll call those expressions u and v, right? Then the derivative of this function is going to be u prime v plus uv prime, or the derivative of the u expression times our v expression plus our u expression times the derivative of our v expression. So right here, looking at our f of x from the previous page, we would say that we can let our first variable expression be u, our second variable expression be v, and then our derivative is going to look like this. It's going to be u prime times our v, and then plus u times our v prime. So right here, taking the derivatives, we would say that we have derivative of 2x plus 1 as 2, and then times our x squared plus 3, and then plus our u of 2x plus 1 times our v prime, the derivative of our v expression, as 2x. Now right here, if we multiply all this out, it should give us our derivative from the previous page, right? So right here we would say that if we do this multiplication out, we're going to get 2x squared plus 6 plus, and then right here we can call this 4x squared, and then right here plus 2x. And of course, when we combine like terms, we can say that our derivative would be 6x squared plus 2x plus 6, which is our derivative from the previous page. So right here, this is the product rule. One of the things I'm going to say about the product rule here is I don't think it's necessary for us to go through and simplify after we get the product rule. Because in fact, this form right here is a usable form of the derivative, right? We can basically go through and plug in to evaluate each of the expressions that we are multiplying, right? And then multiply those constants that we get and then add together to get the value of the derivative. And that is just as quick a way of getting the derivative as doing all the multiplication out and simplifying and then plugging in x values. So right here, when we take the derivative with the product rule, what I'm going to say is we don't have to do the simplification of multiplying things out and combining like terms. I still want us to always do the simplification of no negative exponents and no fraction exponents. But right here, we don't have to actually go through and do all this multiplication out. We just did it in this case to show that we're going to get the same derivative we got in the previous page. So right here, why don't you guys go ahead and try B on your own, and we'll come back and look at this in a second. All right, guys, so right here, if we assign our u to our x cubed plus x plus 1 and v to our x to the fourth plus x squared plus 1, we can go ahead and take the derivative of the product rule, and we will get 3x squared plus 1 times x to the fourth plus x squared plus 1 plus our u v prime of x cubed plus x plus 1 times 4x cubed plus 2x. I don't think it's worth it to go too far into these. I just want, it's such a quick process. Really all I want you guys to do is to sort of make sure that you're getting in the rhythm of taking these derivatives. So right here on our next page, we've got a couple of situations where you can use the product rule. So right here, we'll do this in 2 steps. We'll basically simplify each of our multiples so that we can take the derivative of the power rule term by term, and then we'll go ahead and take the derivative from there. So we'll do first simplification, then I'll unpause the video. You guys can take a look at that, and then right here we'll take the derivative with the product rule after that. All right, guys, so right here, when we rewrite our first function, f, to get it so that we can take the derivative of each of these terms with the product rule, we'll have our 5x squared, that's just 5x squared because we can already take the derivative of the product rule there, and that cubed root of x we can write as x to the 1/3 power. And right here for our second function we're going to take the derivative of with the product rule. We can rewrite that 3x to the 5th divided by 5 as 3/5 x to the 5th plus 7. And then right here in our second parentheses we can say that our v would then be x to the 1/2 minus e to the x, since e to the x is already in the form that we can take the derivative of with the power rule. Why don't you guys pause the video again, and we will take the derivative with the product rule. Alright guys, so for our c, we had our u as 5x squared times our v of x to the 1/3, and when we take the derivative with the product rule, we have u prime as 10x and our v as x to the 1/3 plus our u as 5x squared times our v prime of 1/3 x to the negative 2/3. And then of course we had to take care of fraction exponents and negative exponents, and right here we would get 10x times the cubed root of x plus 5x squared times 1/3 times the cubed root of x squared as our final form of the derivative there. With d, we said that our u was 3/5 x to the 5th plus 7, and our v was x to the 1/2 minus x to the e. And right here, when we took the derivative, we had u prime as 3x to the 4th times our v of x to the 1/2 minus x to the e plus our u of 3/5 x to the 5th plus 7 times our v prime as 1/2 x to the negative 1/2 minus e times x to the e minus 1. And right here, taking care of our fraction exponents and our negative exponents again, we can say that finally our derivative is going to be 3x to the 4th times the square root of x minus x to the e plus 3/5 x to the 5th plus 7 times 1/2 times the square root of x minus e times x to the e minus 1. And again, that would be the final form of our derivative. So, right here we've gone through 2 of the 3 rules that we're going to look at. We're going to do one more rule and then we're going to call it quits. So this last rule we're going to talk about is the quotient rule. So we needed the product rule to take the derivative of a product. And here when we have a quotient or a division of x expressions, our expression u would be our numerator and our expression v would be our denominator, then right here we would say that we need the quotient rule to take this derivative of the division of x expressions. So right here we would say if our function is of the form u divided by v, then the derivative is going to be u prime v minus u v prime over v squared. And notice that that numerator is the exact same as the product rule, only we have a subtraction instead of an addition. So right here, if I'm looking at a, I've got my function as x squared minus 1 divided by x squared plus 1. Right here we can say that our u would be that x squared minus 1, and our v would be the x squared plus 1. And when we take the derivative, we would say dy dx would then be our u prime times our v minus our u times our v prime. So right here, u prime, or the derivative of the numerator, would be 2x times our v, or our denominator, of x squared plus 1. And then right here we would say minus, and then our u, or the numerator, of x squared minus 1 times our derivative of our denominator, which would again be 2x. And then this is all being divided by that denominator of x squared plus 1 on v squared. And that's our derivative, right? So right here, we have a couple for you guys to try, and I'm going to let you guys go ahead and jump in and take the derivatives with the quotient rule. For our b, we have d dx of x squared divided by 1 minus x cubed, which of course is saying the change in x squared divided by 1 minus x cubed with respect to x. So we're going to go ahead and take the derivative of that guy. And right here, our c is just x divided by 2x to the fifth minus 3. Just like with the product rule, when we take the derivative with the quotient rule, we don't need to do the multiplication out. We can leave the derivative in the form u prime v minus uv prime over v squared. We don't need to do any of that multiplication out, because simplifying and then plugging in an x is going to be even more work in a lot of cases than just plugging in an x into those parentheses, getting those values and combining them with subtraction and then division. So right here, why don't you guys go ahead and pause the video and we'll give this a shot. All right, so for our first function with our u of x squared divided by our v of 1 minus x cubed, we've got our u prime v as 2x times 1 minus x cubed minus our u v prime as x squared times 3x squared. And then in our denominator, we've got our v squared as 1 minus x cubed squared. For our second function, we've got our derivative of x divided by 2x to the fifth minus 3 as our u prime of 1 times our v of 2x to the fifth minus 3 minus our u v prime of x times 10x to the fourth divided by our v squared of 2x to the fifth minus 3 squared. All right, guys, so that's it. We'll take a look at some more derivatives next class, and I'll see you then.